Hey, welcome to The Explainer. Today we're digging into something pretty wild in aerodynamics. We're talking about a theory that's almost 100 years old, but it's still, shockingly accurate. And what's really cool is how we're going to look at two completely different ways to solve it. One is all about pure, elegant math, and the other is just raw computer power. And they get the exact same answer. Let's get into it.
So let's start with a really basic question. How in the world do engineers figure out the forces on a wing without actually building one? I mean, think about it. Building a full-scale model is just crazy expensive, and it takes forever. So for well over a century, they've needed a way to predict lift right from the get-go, from the design phase. How do they pull that off? All right, so here's our game plan. First, we'll get a handle on the theory itself. Then we'll check out those two different paths to the answer, the analytical way and the numerical way. After that, we'll put them head-to-head and see just how well they match up. And finally, because it's super important, we'll talk about where this theory doesn't work. Okay, so let's start with the foundation, the theory that makes all of this possible. It's called thin airfoil theory, and it's basically a genius way of taking a super complex problem and making it simple enough to actually get an answer. So what's the big secret here? Well, it's all about simplification. See, instead of wrestling with the entire kind of chunky shape of an airfoil, the theory does something brilliant. It just ignores the thickness. It boils the whole thing down to its very essence, a single curved line called the mean camber line. And by doing that, you get a math problem you can actually solve, and it works amazingly well for aircraft flying at lower speeds. And this is where things get really interesting, because you can tackle this theory from two totally different angles. Think of it like a mathematician versus a computer scientist. The analytical approach, that's the mathematician, right? It's all about finding that one single perfect, beautiful equation that solves everything. Then you've got the numerical approach, the computer scientist. It doesn't really care about elegance. It just says, let's chop this problem up into a million tiny pieces and let the computer crunch the numbers. Brute force, basically. All right, let's dive into that first path, the analytical way. This is all about pure mathematics, a method made famous by Hermann Glauert. Okay, so here's the absolute key to making this whole thing work. It's called the Glauert transformation. You see, the main equation is this really tricky integral that runs along the length of the airfoil, which we call x. It's tough to solve directly. But Glauert had this genius idea. What if we just map that straight line onto a circle? We transform that x-coordinate into an angle, theta. And that one simple, clever trick, it's like finding the key to a lock. It just opens up the entire problem. The process itself is just so logical. It's really elegant. First step, you do that transformation from x to theta. Then the next step is to describe the airflow, right? We need to model how the air is swirling around the wing to create lift. And for that, we use a super powerful math tool called a Fourier series. And when you do that, it spits out these three little coefficients, A0, A1, and A2. And believe it or not, those three numbers hold basically all the information we need. And check this out. After all that calculus and transformation, this is what you get, the final equation for the lift coefficient. It's just beautiful, so simple and clean. It boils down to just 2 pi, multiplied by those coefficients we just found. I mean, that's what mathematical elegance is all about, right? Taking something complex and making it simple. And what's cool is that even when you write code to do this, you're still sticking to that pure math philosophy. Look at this Python function here. It's not just guessing. It's essentially doing calculus. It's taking thousands and thousands of tiny little steps to calculate the exact integral from the theory. So you get the same level of precision you'd get by doing it on paper. Okay, so that was the elegant way. Now let's switch gears completely and look at path number 2, the discrete vortex method, or DVM. And with this one, you can pretty much forget about elegant math. This is all about brute force, breaking the problem down into tiny pieces and throwing a computer at it. The process here is, well, totally different. Step 1, we take that same camber line, but instead of transforming it, we just slice it up into hundreds of little pieces called panels. Step 2 is where the magic happens. We build this massive grid of numbers called an influence matrix. And what it does is for every single one of those little panels, it calculates how its little swirl of air, its vortex, affects every other panel. You end up with this gigantic system of equations, the kind of thing that's perfect for a computer to solve. But hold on, there's a catch. When you're trying to solve a giant matrix like that, things can get messy. You can get weird numerical errors or noise that make the answer totally wrong. So to keep things stable, we use a really powerful technique called singular value decomposition, or SVD. You can think of it as a filter. It solves the system in a super robust way that weeds out all that noise and makes sure the answer you get actually makes physical sense. And if you look at the code for this method, it's doing exactly that. Its whole job is to build that huge matrix A and then just hand it over to a specialized solver like the SVD function here. The computer then does all the heavy lifting to decompose it and give us a stable, reliable answer. Okay, so we've got the mathematician's path and the computer scientist path. Two totally different ways of thinking. So, the big question is, do they work? How do their answers actually stack up against each other? You have to see this. It is absolutely remarkable. We're looking at a classic NACA 2412 airfoil. The analytical method, the pure math, gives a zero lift angle of negative 2.0772 degrees. In the numerical method, you guessed it, exactly the same, down to the 4th decimal place. And both of them are off from the real-world benchmark by less than 0.003 of a degree. It's just an identical result. It's insane. And we're not just talking about one single data point here. Look at these performance curves. This shows you how the airfoil behaves across a whole range of angles. One line is the analytical method, the other is the numerical one, and you literally can't tell them apart. They are right on top of each other. The agreement is just perfect. Okay, so this is all pretty mind-blowing, right? And this is a big but. It's crucial to remember that this theory works so well because it makes some pretty big simplifications. It's not a magic bullet. To use it right, you have to know its limits. So here are the big ones to keep in mind. First, it only works for small angles of attack, which means it has no idea what stall is. It can't predict that. Second, it assumes the flow is totally frictionless, so you can forget about predicting drag. It just can't do it. We already know it ignores thickness. And finally, it assumes the air can't be compressed, which means it's really only good for low-speed flight, think below Mach 0.3. And this really gets to why having both methods is so powerful. This quote from the source material just nails it. It says, "The analytical integration approach serves as a definitive baseline for aerodynamic theory, confirming that exact calculus-based solutions provide mathematically elegant and precise verifications." In other words, that beautiful old-school math solution gives us a perfect yardstick to make sure our complex computer models are actually getting the right answer. So, this leaves us with a really fascinating question to think about. If a theory that's literally 100 years old can be this accurate, what does that tell us? It really makes you wonder how these foundational, almost timeless ideas are still the bedrock that we use to validate, the massive, complex supercomputer simulations that are designing the aircraft of tomorrow.